Okay, thank you so much for the invitation. And like I said, I'm between you and your lunch. So since I'm in the front here, you can get up and get your lunch at any point in time, I'm sure. And I'm not going to worry too much about that. So the two talks before me are great introductions or lead into what I'm going to say. There's going to be a healthy discussion after this, I'm sure, in terms of what we're getting into. And so I was given the topic of observational constraints on modern climate sensitivity, and I think that gets into the climate sensitivity that we're talking about for the last century. And so this idea of long-term climate sensitivity on millennial timescale or the climate sensitivity associated with paleoclimate events is something that is of major interest to us in terms of what's going to happen in 1,000 years and so on. But the data that we actually have is for the last 150 years that's of sufficient quality to make us think about the patterns of climate change and the changes that that are going to be affecting us over the next 50 to 100 years. And so that's what we're dealing with. So the other problem is that when you give a talk like this, you put your slides together and you find out that everybody else has used all your slides. So it's almost better at the end of the day just to stand up and talk instead of working from your slides. So I thought it would be worth a little bit to say, one is, how are we actually estimating the equilibrium climate sensitivity? And I think that this is is this a laser pointer? Yeah. So I say our goal here is that we're trying to match a parameter in a model or the model response to the record of the 20th century, and or you're looking at some climate change in the past, in the historical past or the paleoclimate past, and trying to do the same thing. And so in one sense, the real issue here is what is the model? And if you're a full atmosphere ocean GCM or full Earth system modeler, what you're probably interested in is this one here, the Earth system models. And you have a huge number of parameters associated with the parameterizations, and that's what Dan was referring to at the beginning of his talk. And the problem is that you can't tune or calibrate every one of those model parameters to the 20th century record. So what you wind up doing is looking at the model response over the past 100 years and then scaling that response to estimate what the climate sensitivity is as a result of this. And so you can do that with individual model simulations, or you can do that with an ensemble of simulations. And that's one approach to trying to estimate what climate sensitivity is from the state-of-the-art climate models as a result. There's another spot in here. Well, down at the bottom here, I have the other approach, which I think is sort of what Steve was discussing in his talk, which is using essentially a very simplified energy balance model for the planet. And to all intents and purposes, you have to satisfy that energy balance for the planet, and I think that's one of the take-home points of his talk. And I completely agree with that. The question is, how do you go about doing that, and then how do you interpret the climate sensitivity of that from that estimate as a result? For the energy balance models, that can be an equilibrium parameter. It's just a single parameter lambda, which was in that model. There are more comprehensive energy balance models. The MAGIC model is a classic one. It has two hemispheric temperature boxes, and you have a single parameter lambda in that system, but you're resolving a little bit more of the system. The other approach is to hit in this sort of sweet spot in between with Earth system models of intermediate complexity, and this is the area where I've worked in for most of my work on this. And the parameters that you're calibrating or estimating from this procedure are not strictly climate sensitivity. What you're calibrating are processes which control the feedbacks within the system. And so cloud feedback is an uncertainty in the climate models that was alluded to. And so can you calibrate the cloud feedback in the model and then infer what climate sensitivity is from that after the fact? And so part of the discussion is, as we go through this hierarchy of climate models, what is the one that we want, which ones are the ones that we're going to be using and trusting, and the ones that are most relevant then for the economic discussion, the economic modeling and damages questions that are, I think, relevant over on. So that's my 5 minutes. I'm done. Well, so I guess the other issue here is we have a set of observations for the 20th century. And how are we going to actually use these? This is a slide I pulled out from. I've shown this a lot of times over the past decade, probably. But our goal here is we're trying to calibrate or estimate these internal parameters within our EMIC in this case, and we think of them as climate sensitivity and an effective ocean diffusivity, and the net aerosol forcing, which we were talking about. But we're trying to calibrate given our observations. And our observations that we have are a record of air temperature, upper air temperature, surface air temperature, SSTs. And we also have observations of the ocean heat content. And those are going into these various estimates. The big kicker here is what do we do about the noise covariance, or the variability of the system that you're using to test your, put into your likelihood function, which is then driving the your ultimate estimate of the probability distributions for these various parameters. So the method sort of goes like this, and this is essentially true for all the three methods that I showed previously. You simulate the 20th century using anthropogenic and natural forcings. You vary the values of these parameters in your model. You then compare the individual model responses against the observed temperature changes in what I use as an optimal fingerprint detection algorithm, and that requires an estimate of the climate variability in the system as estimated by this noise covariance matrix. Then you take that goodness of fit statistic, how well is your model able to reproduce the historical record, and create a likelihood function, and that likelihood function is estimated for the different diagnostics that you're using, the surface temperature, ocean temperature, upper air temperature, so on and so forth. And then that finally goes into Bayes' theorem, and then you're combining those likelihood functions with a prior in order to come up with a probability distribution at the end of all of this. So I don't know if this is something everybody knows, but it's something that I think is worth going over for how it sort of plays itself out in the system here. So that now I'm shifting gears a lot, and so I was a IPCC author on the chapter 9, which is the model evaluation chapter, and Dan was showing some results from that with the 20th century climate change for the global mean surface temperature. And for me, when I was as part of the process, one of the key things for me was how are we doing with the feedbacks in the system, not necessarily looking at the global mean temperature in the system. And this is where I think this figure is one of the big figures that makes us think now about the ability for us to model the sea ice distributions, which is one of the major feedbacks to the Earth's climate, the Earth's albedo. And so what we see here now is the sea ice extent in the northern hemisphere at the period in which you have the minimum sea ice extent for the entire for the summer, the northern hemisphere summer. And a few things that are obvious here. One is the range of sea ice extents sort of for the basic state here before we even get into the rapid climate change of the last half of the century is actually quite large. And so that means that the baseline from which you're starting your doubled CO2 experiment is going to be affected by what that initial value is for the Earth's albedo. Then we get out here to the end, and starting in the 1970s, when we actually have satellite observations to track what was happening, that's when we start to see whether or not we're getting the right rate of change. And the distinction between a rate of change of something and the actual change itself, or the integrated change, is what matters. The integration of this over time is telling us what the total reflected energy is, or the total absorbed energy is in the northern hemisphere system that's wouldn't have been there if the ice hadn't melted. That's very different than saying what's just the actual value of the ice extent itself. So there's sort of for the economists, it's sort of a rate and a stock problem in terms of the way you think about these things. energy is a stock. Radiative forcing is a rate or a flux quantity. So are the models getting it right? Well, here in the last part of the century, you see the multi-model mean was discussed as being sort of the best model, and there's a lot of details as to whether that's whether we should believe that or not. There are clearly models that are in here that are getting the right rate, and that's one of the take-home messages, is that there are good models that are doing this right. Not all models are good based on a single metric like the sea ice extent that we have here. So the other one on the bottom here is the Antarctic sea ice in February. Again, that's the time at which the minimum sea ice extent is occurring in the southern hemisphere during the summertime. And what we have here is an even larger range of sea ice extent values. And so our uncertainty in what's happening in the polar regions now becomes much more important. The other figure here was, are you getting the ice in the right locations? The winds in the polar regions are driving and moving the ice around in those areas, and therefore are controlling essentially whether the ice is being pushed up against the continents and remaining in place and lasting a few years, or whether or not it's melting and being pushed around Greenland and then coming into the North Atlantic, and so you wind up with less ice in the Arctic Ocean than you had previously. And again, the models are kind of encapsulating the best guess as to what's going on over the past 20 years. But the range of the models at reproducing this is quite wider than I think we would like it to be. And so can we use that as a tool for analyzing the ice albedo feedback or the ocean ice interactions and various other feedbacks in the system as a result of this? The other issues, how much time do I really have? 5 minutes? Yeah, I had 5 minutes 5 minutes ago. Okay, all right. So a few things here. One is the goal of what we're doing is really trying to match this global mean temperature record that we have here. Many of us use, instead of using the annual data, we use a decadal average or a smooth data set, and that's what's shown down here in the bottom. And the gray bands here are actually the estimates in the observational uncertainty. And so one of my points is that observational uncertainty is much larger than we had thought it was probably 5 to 10 years ago, and so that's coming into play. The other issue on this graph is the spatial extent of how well we know the record over the past 100 years. This starts in 1901 and ends in 2012, and this is the estimated trend over that time frame. So imagine fitting a straight line to this curve over here and then plotting that on this over here as a function of space. And a couple of things. One, we have a clear amplification effect going on over land and in the northern hemisphere. We also have less data down in the Southern Ocean in order to estimate what the trends were at that time frame. And we also have some holes in our data set in the tropics and some areas where we have what are clearly something's going on there in the North Atlantic, which led to cooling over that time, over this 112-year period. Now, is it truly a cooling overall, or is it a large fluctuation that's occurring there? And so a trend isn't necessarily capturing the variability that we see here in the global mean temperature record as a result. Okay. The other big take-home point is the energy content for the planet. And we've all sort of danced around this a little bit. Steve was much more eloquent maybe about this than I am. But the issue here is we now have an estimate of the observed heat content change for the ocean starting in about the 1970 and ending in 2012 or 2011 here. And the picture is so obvious when you look at it this way that over 90% of the energy content is going into the ocean, and less than 10% is going into land and the atmosphere. And that means that if we're going to start actually asking which observations are most important for trying to constrain the long-term integrated energy content, then we have to ask, are we really getting the oceans right? Are we getting the mixing in the oceans correct or not? And despite what's happening at the surface with the uncertainty in the forcing and the uncertainty in the clouds and the aerosols response, if it's not going into the ocean at the right rate, then we're missing something in a significant way. I always like talking about zettajoules, since nobody knows what a zettajoule is unless you actually write it out. Okay, so the radiative forcing picture here from the IPCC. What I liked in Steve's talk is that he showed that the estimate was previously 1.7 or so for the change in the radiative forcing over the last since 1750. And this is one of the issues that gets to climate sensitivity. I'll skip over everything else on here. But 2.6, just to remind everybody, that's the RCP 2.6 scenario. We're only 0.3 of a watt away from that, and that's what we're saying is what we should be stabilizing at if we're going to stay with underneath 2 degrees C. So good luck with that. That's to the next generation, is who's going to be dealing with this, of course. Okay. Radiative forcing and its uncertainty is a big deal as to why there's this big range of, well, partly why the equilibrium climate sensitivity got shifted and it wasn't properly described, or properly, the uncertainty in this term gets thrown around a lot. The issue with the radiative forcing, the effective radiative forcing for cloud adjustments to aerosols is the language which is now used in the IPCC. It's no longer the direct effect or the indirect effect or the semi-indirect effect or the semi-direct effect or any of those which are all in the literature. The idea is that you have these rapid adjustments to cloud environment. And so the result of that is all of these terms here are now incorporated into a single estimate of the change in the radiative forcing. That, as you saw, was much weaker in terms of the cooling effect to the aerosols than it was previously. That leads to a larger radiative forcing over the 20th century. The same thing, though, as you saw, was true for the estimate for the greenhouse gas forcings. We went from, I think the number was 2.9 for the 2.8 for the AR4 to 3.3 for the AR5 was the numbers that you showed in your talk. And therefore, the radiative forcing now has been increased from the total. I'll go back to my little note here. The total number went from 1.6 to 2.3. That, in and of itself, is a reason that the climate sensitivity... What? 1 minute. So that, in and of itself, is a reason that the climate sensitivity was decreased, and part of the reason is what is leading to us to sort of start to question where is the inconsistency between the climate models and what we're getting out of these transient, from these other estimates. Let's see. That's all that. Somebody else can talk about that later. The one thing, this is the result from Otto et al., which tried to summarize in a very similar way to what Steve said, which is taking equilibrium climate sensitivity as a simple linear algebra problem. And I have my issues with that, and we can talk about those later. And one of the reasons for that is because of what I've done with a simple model. I had 1 minute, Klaus, so sorry. So I took one of our MIT IGSM runs, and so that's the integrated global systems model, the climate model component, and we ran it with a climate sensitivity which is set by a change in the cloud feedback. It has a significant amount of internal variability, so it looks very much like the real world. We also set the climate sensitivity to be 3 degrees. We set the aerosol forcing to be alpha equals 1.7, so that matches. We can then go and ask, what is the running through one of these Monte Carlo Markov chain model estimation procedures? We get a cloud of points as to where the values are that best match that record of observations. So this is a pseudo observations problem, a perfect model experiment. The plus up here is where the model should be at 3 degrees. It's down here at 1.6. This estimation procedure is failing for some reason at being able to reproduce what the climate model is telling us it should be. This is a serious look into whether or not our procedure is capable of doing what we expect. Over here, this is climate sensitivity on this axis, the alpha parameter here, and that's actually the point where it should be getting. We're getting a value of 1.6, an alpha scaling of 3.2, and what the question is, what's missing? Well, one of the issues is global information. The global picture is not enough. I know I have less than 1 minute left. And so climate sensitivity here, if I take just global information and take all of these other observational uncertainties, include it, I get this value up here. If I take hemispheric data, climate sensitivity starts to shift to a higher value. If I use zonal data, which includes the difference between the pole and the equator, and this polar amplification factor, I wind up down in this picture here. And the aerosol forcing estimate from these inverse methods is giving us a very wide range of the aerosol forcing for the global case. It starts to tighten up until we get down to the case for where we include the hemispheric or spatially resolved information as a function of latitude. So this is starting to tell us that there is data there that we can use to estimate climate sensitivity and the aerosol forcing and so on and so forth. Are we using it well? I think by thinking about it from a global mean perspective, we're not. I think we have to be going to these higher order methods, and the statistics are funky. They need some, a decent statistician to help us out, as Klaus and I both know, working on some of these things with our friends at Penn State. But that's part of the picture. And then the last one here is we've taken the observational uncertainty in the HADCREW T4 data set, 100 different simulations. They created an ensemble, which are all plausible reconstructions of what happened over the past century. And I ran our calibration tool with those 100 different cases. And these are now the spread of the distribution. There's 100 curves on there. And that now is sort of the estimated uncertainty. One in what the peak value or the mode is almost a difference of maybe a full degree there. The aerosol forcing is still in a fairly tightly coupled, but we still have this long tail, and it shifts along. And this is just one other example of where these uncertainties are starting to show up. And I apologize for keeping you hungry. And I'll stop there.